Well, I've got about 40 or 45 minutes right now, so section 11 will either be divided into 3 parts or maybe one short recording and one longer one. We'll see. But to get a start on it anyhow, section 11 is about waves. A wave is defined by what I said on the first line there. It's some sort of a disturbance moving through whatever kind of medium it moves through. It's not necessarily periodic. I mean, the stereotype that everybody has in their head is waves at a beach, where one comes in and then the next comes in and it just repeats itself over and over again. And that sort of thing is pretty common with waves. But you could have just a single wave wash up on a beach without it having to repeat over and over. You know, like if you're standing next to a pond and somebody threw a stone in it, or even just like with a sound wave, just a single pulse of sound like that isn't really, well, maybe the simplest example would be to just picture a line of dominoes, okay? Just somebody's lined up hundreds and hundreds of dominoes, and you knock over the first one and it knocks over the second one, and then that knocks over the third one, and you have this disturbance propagating along this line of dominoes. And that actually is not terribly different from how sound waves work. As I sit here talking, my vocal cords in my throat kind of knock around the air molecules that are touching them, and then they bump into the next air molecules, and then, you know, one molecule hits the next, hits the next, hits the next, and that disturbance works its way across the room until it reaches somebody's eardrum. And then the motion of the air makes the eardrum move, and there's a mechanism inside of your head that senses the motion of the eardrum and interprets it as sound. So a disturbance of some kind going from a source, you know, a source over here in one spot to somebody who sees it or hears it or whatever over there, a moving disturbance. They can be divided up into at least a couple of different types called transverse and longitudinal waves. I've got a demonstration here to show you the difference. I'm going to pause it while I get the camera aimed the way I want. Okay, let's see how this works. I think maybe it'd be best if I tilted that a little, see if I can hold the camera with one hand and the slinky with the other. Now, what it says there on the handout is that a longitudinal wave is one where a little piece of the medium moves parallel to the direction of propagation. So what I'm going to do in a moment is I'm going to move my hand around. My hand is the source of the waves. The waves will propagate along this slinky. That would be the medium of the wave. And if you watch one particular coil on this spring, on the slinky, if I'm moving it like this, those are longitudinal waves, okay? Goes back and forth along the direction of propagation like that. Sound, for example, is a longitudinal wave. As a sound wave goes across the room, the air molecules get squashed together and then pulled apart, and then squashed together and then pulled apart. As that happens, the air pressure goes up and down a little bit, not by any significant fraction of atmospheric pressure, unless it's some terribly loud sound that's going to blow all the windows out of the room or something like that. But anyhow, that's a longitudinal wave. Some of the waves produced by earthquakes are longitudinal. Some of the waves produced by earthquakes are transverse. And they are like this, okay? So now, if you watch one particular coil on the slinky, it goes side to side instead of back and forth, okay? So longitudinal, or I just said that completely backwards. This one's longitudinal, this one, that's transverse. Back to the previous camera angle. And of course, it's going to be ornery about focusing again. So focus on my hand. And okay, that worked. Examples of transverse waves. Light is a transverse wave. The electric and magnetic fields vibrate perpendicular to the direction that the wave is moving. Waves on strings, such as the strings of musical instruments, guitar strings, piano strings. The string vibrates crosswise when you set waves moving along it. Water waves, I said sort of. Water waves are actually complicated. On the one hand, it's nice to talk about water waves in an introductory course because they're the ones you can actually see. People have gone to the beach and splashed around in the waves, whereas light and sound and things like that are kind of intangible. But on the other hand, water waves are not that nice to talk about in an introductory course because they are complicated compared to something like sound, for example. The real story with water waves is if you had really good eyes and could watch one water molecule move as the wave goes by, what it actually does traces out an ellipse, okay? So I have transverse sort of, because to a casual observer, you're standing there on the beach and as the waves go by, you see the water go up and down, and that's probably the first thing you notice. And a wave that's traveling horizontally that makes the medium move vertically, that would be a transverse wave. But if you examine things a little more closely, not only is the water going up and down, it's also going back and forth. So you've got components in both directions. Longitudinal waves, I already mentioned sound is longitudinal. And I've messed up the focus again. Well, when I get the thing to, oh, there we go. Didn't take that long this time. As I said, a wave does not have to be periodic. I could take that slinky and flip it just once so that a single pulse moves along it. But if I do shake my hand back and forth repeatedly so that I create a wave that periodically repeats itself, you might get a graph. If I'm shaking it to make a transverse wave, at a given instant, like if you took a photograph of it, the slinky might go back and forth along a path like this. Or if you're looking into the side of an aquarium at a water wave, you would see the surface of the water following a path that looks a lot like this. Even if it's a transverse wave, or why do I keep doing that? Even if it's a longitudinal wave, this then would not be a literal picture of the wave like you could take with a camera or something like that. But if you graphed how far each coil on the slinky was from its equilibrium position. Well, you know, these here are to the one side of equilibrium and these here are to the other side of equilibrium. And if you graph the displacement of each point in the medium, you get the same graph that you would with a transverse wave. So the places where it tops out are called crests and the valleys are called troughs. And I've labeled the distance from one crest to the other with the Greek letter lambda, which is the symbol usually used for the wavelength. Now, if you go back, oh, I can't remember, there was probably a graph similar to this one somewhere in section 10, where I had what looked like the same thing labeled with a capital T for period. If there wasn't a graph like that, there could have been. The difference is that graph with the period on it would have seconds, time, on the horizontal axis, whereas here you'd have meters on the horizontal axis. The period is the time between one crest. Well, it doesn't have to be a crest. It could be trough to trough or any point on the pattern to where that point repeats again. But going with the crests, the amount of time between crests is the period, as in you've waded out into the water with a stopwatch in your hand. As the waves go by you, you start the clock as a crest passes you, and you stop the stopwatch as the next crest goes by you, and that would be the time for one complete vibration of the surface of the water. That would be the period. The wavelength means if you're standing where one crest is and your friend is standing where the next crest is at a given moment, I mean, it's a moving pattern, but at a particular instant, if you're here and your friend is over there and you're 5 meters apart, the wavelength is 5 meters. So I guess I was going to write some of this stuff down on the blackboard. Or maybe no, I wasn't. I don't actually see it here in my notes anywhere. Oh, yeah, that's further down the page. Time to boost the page. So the reason I wasn't going to write it on the blackboard is because it turns out it's further down the page here. Lambda is the Greek version of the letter L. L for length, as in the length of one wave in the whole series of waves that's going by you, as illustrated on the picture. The frequency of a wave means the frequency that the medium vibrates with. Okay, it means the same thing it did in section 10. Likewise, the amplitude is the amplitude of the medium's vibration. Okay, if from there to there is 15 centimeters, then the amplitude is, you know, center line to either extreme. Same thing it meant talking about vibration in section 10. Incidentally, I should probably clarify one thing. I started out the video for section 10 with a mass bouncing up and down on the end of a spring. That is not an example of a wave, okay? That was an oscillator. It was something that was vibrating, but well, it's disappeared off the top here now. But remember, a wave is some sort of a disturbance that goes from one place to another. A mass bouncing on a spring doesn't fit that description. It isn't going anywhere. It just sits there on the stand that I had the spring hung from. A wave is a moving disturbance. There's a relationship between waves and vibration in that typically the medium vibrates as the wave goes by, but they're two distinct things that you don't want to mix up. A pendulum is not an example of a wave. So anyhow, in the case of sound, the way you interpret its frequency is as the pitch. If you go along a piano keyboard, pushing different keys, as you go from the low notes heading toward the high notes, the frequency of the sounds that you're making is increasing. High notes are high frequencies, low notes are low frequencies. In the case of light, the frequency is the colors of the rainbow, to be specific. If you want to start talking about colors like brown, that's a mixture of different frequencies, but something like, well, blue, for example, is a higher frequency than yellow, is a higher frequency than red. Amplitude. In the case of sound, it's the loudness. A loud sound, you might have a quiet sound that makes the air molecules go back and forth that much. A louder sound would make them go back and forth farther. Bigger amplitude, louder sound. In the case of light, the amplitude is the brightness. Direct sunlight is waves with a considerably larger amplitude than if you're in a dark room holding a candle. Okay, so other properties of waves aside from the terminology that carries over from last week. I already mentioned the wavelength. The other thing would be the speed of the wave. This would be like the speed of sound or the speed of light, or if you're sitting on a dock watching the waves go by on the surface of a lake, if you watch one particular wave, one particular lump on the water, how fast is that moving across the surface? How many meters per second is it covering as it heads toward the shore? There is a very useful relationship. Actually, this would be one of those things where you have to remember it. It's not on the formula sheet, between wavelength, frequency, and speed. And it only takes about 20 or 30 seconds. Well, of course, when I say that, it always turns out to be 2 minutes. But it takes some fairly brief amount of time to explain where it comes from, why it's true. And that little story goes like this. Let's start with the fact that in a time of one period, the wave moves a distance of one wavelength. If you and your friend have gone to the beach, and maybe your friend is a little taller than you are, and whatever reason, they've gone out further, so that maybe, if the wavelength is 20 feet, your friend is 20 feet further from the shore than you are. Picture that, okay? So, at one particular instant, just as the waves are topping out where you are, the next wave is topping out where your friend is, because you've separated each other by a distance of one wavelength. So if you're at one crest, your friend is at the next crest. Well, what happens next is that where you're standing, the water level goes down, and then it comes back up again. And that's the end of one period. The surface of the water has gone through one complete cycle. Well, when the water comes back up to your chin again, that happens at the arrival of the wave that started out where your friend was, okay? So in that time of one period, this wave pattern moved over by one wavelength. let's stick that little fact into from probably the first page of your notes back at the beginning of the course. Distance equals speed times time. Delta x equals v times t. Meters per second times seconds gives you meters. Okay, well, if the wave moves a distance of one wavelength and the speed of the wave is v, it moves a distance of one wavelength in a time of one period. But for reasons that I can't exactly explain, people seem to want to talk about the frequency rather than the period. Well, okay, doesn't make any difference. The frequency is the reciprocal of the period, or the period is the reciprocal of the frequency, I guess is the way to say it here. Seconds per cycle is the reciprocal of cycles per second. Well, I'm just going to multiply both sides by f because it's nicer when you don't have a fraction to look at. So, the moral of the story is the speed of a wave equals its frequency times its wavelength. And you're supposed to remember that. And with, as with other formulas that you might have to come up with out of your head instead of looking at it on your formula sheet, one thing that can help guide you is a little bit of dimensional analysis, because, you know, we get in the middle of a test and sometimes people, they can't quite remember how it goes, and they'll put v equals f divided by lambda or some other random combination of the variables like that. Well, think about the units, okay? You've got cycles per second times how many meters per cycle, or, you know, how many meters per wave, whatever way you want to say it, cycles per second times meters per cycle will give you meters per second. If the equation you've written down doesn't make sense dimensionally, if the units aren't working out correctly, then you better stop right there, because the rest of what you do with it's just going to be garbage. So we are to example number 1, which is just slightly below the bottom of the picture. Okay. This is actually something that we do in Physics 132, those of you who are coming back in the spring for the second part of the course. What we're doing at that time is I'm just giving you a few exercises to familiarize people with which buttons and knobs do what on an oscilloscope. And one of the things that's kind of fun to do for that is to just hook up a microphone and make people hum into it and measure the period and frequency of their own voice. It's, you know, kind of fun here to sit at the front of the room and watch people. Well, anyhow, so that would be how you'd actually go about measuring this. You've got a little graph in front of you, and you measure the time for one vibration on that graph. And 5 milliseconds would not be unusual for a human voice. Actually, that's going to turn out to be about 200 hertz, which is a fairly typical number for the female students. The guys tend to run a little lower, although what happens sometimes is they'll bring their paper up And it'll be like, oh, the frequency is 210 hertz. Oh, let's see, that was you, wasn't it? And I'm pointing to the young woman in the group. And the guy looks at me and goes, no, that was me. So anyhow, people can, they can hum different notes, but the range that the guys tend to settle into tends to be a little lower, as you probably noticed. Anyhow, based on that one piece of information, first of all, calculate the frequency of that sound. I'm going to do it right there. The question gave me the period, and it asked for the frequency. Well, from last week, frequency and period are related to each other like this. The only trick is that the period was given to you in milliseconds. If you want the frequency to come out in cycles per second, not cycles per millisecond, you have to convert. Five thousandths of a second, 5 milliseconds. "200 cycles per second." As I said, not at all unusual for a human voice. Then it asks for the wavelength of that sound. Well, that's going to be this thing that I just came up with over on my left here. V equals F times lambda. Lambda is the wavelength. That's what part B is asking for. So rearrange it a little bit, and you've got lambda equals speed divided by frequency. Question says it's a sound wave. The speed of sound is available on your reference handout. One of the pages toward the, I'd have to get it out and look at it, but I think it's the same table where you look up the mass of the earth and things like that. Just, miscellaneous physical data. Wherever it is I've got there, speed of sound in air at room temperature. The speed of sound is somewhat of a function of the temperature. So this would depend, when I say room temperature, it depends a little bit on how warm you keep your room. If you haven't paid your fuel bill, the speed of sound at 0 degrees Celsius is 331 meters per second, okay? On the other hand, if you keep the house a little on the warm side, you might have 345, 347, something like that. But, I think this is appropriate for something like, if I remember right, something like 69 or 70 degrees Fahrenheit, somewhere in that general range, give or take. So we're going to go with that, unless the question you're working on says something to the contrary. From part A, the frequency is 200 hertz. Which gives you a wavelength of 1.71 meters. About that far, it doesn't quite fit. Yeah, that's just about what I can fit on the screen at once. As I said, sound is a compression wave. So what that means, a wavelength of 1.7 meters, as the sound wave goes by, the air molecules get compressed together and then pulled apart, and then compressed together and then pulled apart. The wavelength would be the distance from one sheet of compressed air, slightly compressed air, to the next, okay? Somewhere in the middle here is where the pressure would be a minimum, and 1.7 meters apart would be the distance between the maximum, as you know, as the wave goes along. What have we got next? It says, I'm not going to bother pointing it over there for just to read you one sentence. It says the equation of a one-dimensional sinusoidal wave moving along the x-axis. So, you know, it's an introductory course. Let's try and keep things functions of the minimum number of variables. If you want to talk about a sound wave propagating in 3 dimensions, like my voice moving around in this room, that would be a function of 4 variables, x, y, z, and the time. If you wanted a function for the displacement of the medium at any point in the room. So yeah, let's leave that sort of thing for a more advanced course and say that what we're talking about is maybe a wave traveling along a string, which would be the same kind of thing as the wave on that slinky that I was waving around a few minutes ago. Or if it's a water wave, instead of spreading out on the surface of a pond, maybe you've got a water wave in some sort of a trough, like the gutter on the side of somebody's roof. Got some water in it, and there's a wave traveling along that can only go in the x direction. It can't spread out in the y direction. So for the sake of simplicity, a one-dimensional wave would be of this, assuming it's a sinusoidal wave or a harmonic wave as it's sometimes called, that refers to the shape of the wave, that the wave is shaped like a sine wave or a cosine wave. Let's assume that it's going in the positive x direction, okay? You know, positive x-axis is in that direction, that's where the wave is headed as it's going that way. I'm going to use sine for this. If you're a cosine fan, you could do that. Using cosine would just change the phase angle. Y here means the displacement of the medium. In other words, if over here, if that's the surface of a pond, well, not a pond, the water in a trough, like I was saying. Y means at some particular time, at some particular place, how far is the water level at that point above or below equilibrium, okay? So as the wave goes by, the surface of the water goes up and down. So how far has it been displaced? That's what the Y stands for. X is what location are you talking about? Okay, are you talking about the surface of the water vibrating here, or are you talking about the surface of the water vibrating there, or where? And of course, T is what time is it? V is the speed of the wave, and phi is a phase angle. So this factor here, 2 pi over lambda, that's what makes the function repeat itself after a distance of 1 wavelength, okay? The sine repeats every 2 pi radians, and this factor of 2 pi over lambda makes it repeat when x changes by a distance of 1 wavelength. The minus Vt term in here is what makes the pattern progress further to the right as time goes by. Let's say, for example, let's say that at t equals 0, there was a crest right at the origin, okay, that whatever the other numbers are, they work out in a way that makes the sine equal to 1 at x equals 0 when t equals 0. Well, that crest that occurs where this is equal to 0, a little later, when the time gets bigger, a bigger x minus that is where that 0 will be. And at a still later time, you'll have to subtract it from an even bigger value of x to have 0. So this crest that occurs where this is equal to 0, that's going to get farther and farther to the right as time gets bigger and bigger. Okay, as t gets bigger, x gets bigger, and that particular feature propagates toward the right, as long as that's a minus sign. If you want a wave that's going toward the left instead, then it would be the same function, except you would have a plus sign here. Okay, so x plus Vt if going left. Let's make a few substitutions into this, and then in a few minutes I'll be out of time for right now. So basically what we're going for now is a more concise notation. At some point in the history of the subject, somebody had just written 2 pi over lambda for about the 15th time, and you know, it was only 10:30 in the morning. So they said to themselves, you know, rather than have to write all of that, I'll just write the letter k. Let's define k to mean 2 pi over lambda, and then it'll just be k times all of this, and that'll be more compact and easier to write. And that somehow got the name wave number. Or sometimes people call it the angular wave number. Just plain 1 over lambda sometimes gets called the wave number. And anyhow, for our purposes, 2 pi over lambda, that's k, and that goes in there. And then there's one we've already seen before. From section 10, there was the so-called angular frequency, 2 pi times f, represented by the letter omega. Notice it's called the angular frequency. And notice that since f is equal to v over lambda, from what I was saying a few minutes ago, well, 2 pi times v over lambda, that's the coefficient of the time. So 2 pi over lambda times x becomes kx. 2 pi over lambda times v becomes omega, so you've got omega times t, and so my general form for a harmonic wave looks like that. The displacement of the medium as a function of where and when, a sine of kx minus omega t, as in section 10. If you're quick enough with your stopwatch to start the time at the right instant, you can get rid of the phase angle. So I think that's where I need to leave this off right now. The first thing in the next recording will be 11-2, the example. And of course, once again, just to repeat myself, if the wave is going the other way, if it's propagating toward the left, then you have a plus sign here. Signing off.